Welcome. Today we are going to cover engineering economics. It's a multi-part video, meaning that we actually have two presentations to cover all the details of engineering economics. So we'll start off with some of the basics today and some of the terminology, and then we'll move into more detailed calculations as we go forward. Here's our outline. Time value of money. So hopefully those of you who are graduating or near graduating or starting to save for retirement, you sort of understand the concept of time value of money and that whole quote-unquote magic of compounding. So that way you don't have to put in $1 million to have $1 million when you retire. So we'll talk about that. We'll talk about cash flows because the business obviously has to understand the flow of cash. There's no business that can run on negative cash flow. Otherwise, they're borrowing money, and things don't happen very quickly when you're borrowing lots and lots of money. So you always want a positive cash flow, and so that's one of the things businesses are very sensitive to, making sure they have positive cash flow. Comment or question?
Isn't that exactly what Uber is doing?
Pardon me?
Isn't that exactly what Uber is doing, running off of negative cash flow?
So the question is what Uber is doing is negative cash flow. So the difference is it's not actually negative cash flow. What they're doing is they're using investors who are investing in the company with money up front, and then they're getting a piece of the pie, so they're getting some stock. And then the idea is that they actually, even though they show a quarterly loss essentially, but they're still getting cash to pay all their bills because the investors are continuing to dump money in it. So that's why we went to an IPO. I think Uber just did an IPO recently where they were hoping to raise $50 billion because they issue a certain amount of stock, and then that stock brings in cash that then they can use to help balance the books. So their cash flow still needs to be positive. It's just that they're borrowing money against the shareholders, essentially. And it's an interesting thing because if you don't pay back the shareholders, there's different types of stock. There's some just based on the value, and then there's some that actually is a piece of the company. Most of the stock that people purchase actually is the stock that's not guaranteed to have any value. So you're getting a piece of paper, essentially, that could be worth nothing. And that's the risk of owning stock in a publicly traded company. Up until a company goes public, so they do their IPO, they are usually having investors. Sometimes they're called angel investors, but they're usually venture capitalists who are looking to make huge returns, 6, 7, 800% after 2 or 3 years. So they take a lot of flyers on companies, hope that they'll work out, and then a company like Uber, although Uber is not necessarily trending in the right direction, but a company like Uber would focus more on trying to grow, and so they'll invest, they'll give $10 million, and then they'll hope the company will be worth $50 billion, and so they'll get $3-4 billion out of their investment, essentially is how it works. So that's how companies actually can raise capital when it's tight. Tesla, for example, has had quarterly losses for many, many years. Why are they still continuing to run? Why were they able to build the Gigafactory? Because they issued stock, and then investors would buy that stock, and then they actually get cash from the sale of that stock. So the cash flow is still positive. They're just giving IOUs, essentially. That's sort of what the stock means. We'll look at a discount rate. A discount rate is another way to say interest rate, but you're basically going back in time instead of an interest rate. Sort of looks at things going forward in time. A really nice way to compare investments is net present value. So you can compare option A and option B, and the one that has the higher net present value is the easiest, is the option to go. So it's a very effective, easy way to do it. Uniform cash flows, for some of you in the room, maybe you own a house, maybe you have purchased a car, you've been doing uniform cash flows and you probably didn't even know it, right? When you borrow money to buy a car or lease a car, you're getting a fixed charge, right? You're paying a fixed amount to pay back that vehicle or that home, and it never changes, right? Now, you may change in terms of insurance and property taxes, like if you own a home, because a lot of those have to go in escrow, but the actual way that you figure it out is it's a fixed cost to pay the loan back, and that's the whole thing that we're very comfortable with. We like to pay a uniform amount. Even if it's a worse deal, we still prefer to pay that $300 or so a month to pay off our lease. And then we'll look at equivalence. For those of you who are engineers in the room, equivalence is essentially the idea is you can have one option or another option and they look the same, at least in terms of the economics. They don't actually have to physically be the same. They could be completely different horizons, completely different cash flows, but when you compare and look at a same instant in time, they are equivalent to each other, so there's no difference between either option. So any renewable facility, any generating facility, regardless of its purpose, you have to be able to figure out what the financial implications are and then decide whether to build or not. Now, with renewables, it's a little bit different because in specific in the state of Maine, there's been incentives the government has issued that we're going to have, I don't know if it's $200 million or 200 megawatts of renewable energy or solar projects that are being done in the state of Maine. So there's financial incentivizing happening, which is they're going to get paid, excuse me, a higher rate for that PV power than it would be that they could normally get, because PV power is not, at this point, cost competitive with conventional technologies, combustion turbine technologies, et cetera, et cetera. So they're incentivized to do that because governments are recognizing that there are benefits other ways, reduction in CO2 production, power that's being produced locally, losses on the system are reduced, perhaps more reliability because you have generation that's near the load. So the idea is that you actually have those benefits, but you can put a dollar amount on them and include that. So the dollar amount should at the very least include what we would consider our payback. If there is no payback, then we can't even invest, right? Because somebody's going to have to pay for the equipment costs and the construction costs are doing it. Also, you would like to do a reasonable profit. So with generating assets and utilities, they are typically have to be reasonable. And the main reason why reasonable is because a lot of this is regulated by the PUC. If gouging is happening, the PUC has access to a lot of this information, and you can pretty quickly find yourself in some trouble because of price gouging. Whereas the stock market, it's a free-for-all. Sometimes the stocks go up, 200% in a day, and there's no such thing as gouging in that. So it is what it is. So the generation, we have a reasonable profit, and reasonable is dependent upon who you're talking to. You've got two costs, and we talked a little bit about this previously. We have a fixed cost. So again, that's that uniform cash flow, paying back the facility, paying back the construction costs. The variable costs tend to be the more generation we have, the more variable costs will happen. In many renewable technologies, variable costs don't change. For example, if you have a PV system, and it doesn't matter if it's running at 100% power or 80% power, the equipment isn't under a much more severe duty. There's nothing rotating. There's nothing that is being damaged because you're running at its full output. So variable costs in a PV system don't tend to change that much. In wind, obviously, if a wind turbine's running at a much higher capacity factor than anticipated, you've got bearings that are going to need more maintenance. You're going to have mechanical systems that are just going to have more wear and tear on them. So if you don't have rotational elements and you're not buying fuel, your variable costs will tend to be fairly uniform or fairly fixed. So we've already talked about our fixed charge rate. So that's essentially assuming we're going to pay back the plant or the construction of a facility in perpetuity. So that 10% or whatever we did a few weeks ago, we'll constantly pay that back. That's always going to be paid back. And so that's our fixed charge rate. So that's essentially an interest rate that you're just continuing to pay off the interest, essentially. We also did dollars or cents per kilowatt hour calculations to figure out how much you can actually charge or what you need to charge to break even on any particular facility. So we've done these. Now we're going to expand it into doing a more detailed preliminary evaluation. Okay, this is not intended to be all-inclusive because when you look at some of the engineering economics, you have to start looking at some more advanced analysis for a plant to go. And in the next slides, next class that we have, we'll actually discuss those specific topics of what are the different, what's the software that's available to you for free to do that. So how do you reduce costs? You can do supply side, right, which is make better, cheaper power generation. That's increasing the supply side power, which essentially, hopefully, means you're reducing the power cost, reducing the cents per kilowatt hour to make. Demand side management, there's not a lot we can do. We've gotten pretty efficient with our energy usage, perhaps switching to more efficient energy lighting. So in this room, it's probably fluorescents, which tend to be fairly efficient, but you can consider moving to LEDs. You can also have occupancy sensors. You can have those turn off. motors and whatnot, there's not a lot of efficiency improvements we can have there. Perhaps turning down your thermostat, right, and running that more efficiently, or using a heat pump, which actually has a higher efficiency than 100%, right, because it's taking energy out of the system, as Professor Dvorak talked about. So you can take power there and you can use that energy and get it cheaper, but we're really not pushing efficiencies all that much more. Until some newer technologies come around, we won't necessarily see that. But this energy management really is just time of use. So how can we improve the time of use of that? So when do you charge your electric vehicle? There's a number of charging stations on campus, and I'm sure you've seen them when you're driving at malls and such. They see them every once in a while in a location. Well, when you charge the car, has a very big impact on the grid. If you're charging a car, and a Tesla can charge at 120 kilowatts, so a pretty high rate, if you have 5 Teslas all charging at 120 kilowatt, you're pulling, what is that, 600 kilowatts, which is a fairly sizable load. That increases the load on the system, which means you have more expensive and less efficient generating equipment that is online. So if you could move those charging to the evening, for example, your grid is very lightly loaded, it's not having the same level I squared R, and then you could use some of the lower cost, more efficient energy services or energy support system for that. So time of use is going to start to be a much, much bigger thing, mainly because of electric vehicle charging. If you look at some of the work that's being done in California in particular, they're going through massive transformation for their grid because of all the power that's being consumed by electric vehicles. And 120 kilowatts sounds like a lot, but I think Audi is looking at a 190 kilowatt charger. And as we use vehicles, trucks, for example, heavy-duty trucks, semis that can pull a 100,000-pound tractor trailer for 500 miles, those are going to have to charge essentially overnight. And that 120 kilowatts, that's not going to be sufficient. So 200, maybe even 300 kilowatt charging rates, which is really going to tax the grid. And those are going to have to be done at night, not during the day. Question here.
Yeah, so maybe not in California, but throughout the world, I'm sure there's places where they have a lot of electric vehicles. Have they ever had a limit?
So the question is whether they have a lot of electric vehicles, do they have a limit? There are none that I'm aware of. The limits are essentially, so if you go out to California, and I was there over the summer, and they have fairly large charging stations with maybe 20 ports to charge. And depending on the number of vehicles charging at the same time, the chargers themselves will monitor, I believe they're monitoring the voltage on the overall system, and if the voltage starts to drop too much, the charging system will reduce the amount of power that's going out to each individual vehicle. So it doesn't limit them entirely. You've got 28 stations, and if 28 are used, then you have to wait in line. But if all 28 are being used, you're not going to run at 120 kilowatt. You might get down at 10 or 5 kilowatt charging rates. So they'll just reduce it based on the capacity of the incoming system. So they're not going to limit it. They're not going to say, no, you can't do it. They're just going to limit you in terms of ramping you down. So you know what? You're not going to charge your car up fully in 49 minutes, and that's something that you have to include in your destination. Because if you have a Tesla, you go from point A to point B, you can put on their mapping software to get anywhere in the world. Well, North America, right? You got to drive. You can't go over the water. But they actually show you the route to take based on where the charging stations are located, because they assume, hey, look, you're going to drive 300 miles, you're going to stop, have a bathroom break, maybe get a snack because you've been driving for 5 or 6 hours, so you can charge your vehicle back up in 49 minutes. Well, what if everybody else is doing the same route as you are, and you get there and it's going to take you now 5 hours to recharge your vehicle? So that's a complication in terms of what's happening. So you're going to have more charging stations, larger charging stations, or you're going to have businesses like the university that has an opportunity where you can do it. So university can actually start to charge and potentially make money on setting up charging stations on campus. So that's kind of what's going to happen. And you're going to start to see the electrical grid grow bigger because of more electric charging. Right now, we don't think about it, but think of the gas distribution network. How many gas stations are in your hometown? Pardon me?
5. I don't know, 5.
5? I'm thinking in Orono, there's probably 10, 15 in Orono alone. And Orono is a fairly small town. So you figure that has to be all converted to electrical stations and the distribution that would need to be done for that. So fairly significant changes in the electrical distribution system. So if we all switch to electric, we're going to have some challenges associated with that. So just put a charging station at your house, charge at night, make sure it's a 240 volt, 30 amp, it's a level 2 charger, and you can avoid a lot of these time of use stuff. The other thing about the distributed resources are what are the environmental and social costs. So depending on what your beliefs are, does fossil fuel consumption create greater environmental issues on the world? That's a debatable question, and it's a political question, so I keep my opinions to myself, but that's something that, depending on where you live, that might be a bigger deal. So environmental issues, social issues, do we want to have those, do we want to be buying power from a nuclear power plant, or do we want to buy it from a coal plant? So those are the social aspects of it. And all those factor into what are you willing to pay for, I say distributed resources. Anything could be a distributed resource. You could put a diesel generator on campus, and that would count as a distributed resource. But what we're really focusing on is renewable or alternatives, right? Because you're not going to see a lot of people putting reciprocating engines, because those aren't very fuel efficient and they're not very cheap. So most of the distributed resource technology you're going to see are going to be renewables. PV is the biggest one that you're seeing now, because you can put a 5 megawatt PV farm up for probably $3 million, and it runs with very little interaction with people. There may be some pushback, but you get the idea. So a couple things about our bills. So we, as individual consumers, our bill is pretty simple. Our bill basically has two components of it. We pay for the energy that we use, right? So you're paying per kilowatt hour. But in that, in Maine at least, and most of, well, actually all of New England, there's two parts of the energy consumption. There is the actual energy supply. So some generator someplace has to get paid for the actual energy that they put on the grid to service your needs. But also, the utility companies have to be compensated for providing the wires to get from that generator to your home or to your load. So your bill actually has usually a energy charge as well as a utility charge. Sometimes it's called a distribution charge. Sometimes it's called a connection charge. It depends. Not in Maine, but in some other states, you can actually use time of use meters, which again is changing quite a bit, because it used to be if you wanted to save a few dollars, you'd run your dryer after 9 o'clock at night, because most people were starting to wind down in terms of their energy consumption, so they use far less power at night. More power is available for cheaper generation. You would run at night. That's flipping a little bit, and if you go to California and you go to Vermont, they actually have lower electricity rates during the day, believe it or not. During the daytime, when you have bright sun, you get a lot of PV, you can put out massive amounts of kilowatt hours that's available to you. So you're starting to see that they're actually charging lower demands or lower costs during the day. And just at like 5, 6, 7, 8 o'clock, depending on the time, when the sun's starting to go down and the PV effectiveness starts to drop dramatically, that's when your prices are starting to spike. So it used to be you would charge the highest prices between 9 and 5. Now you're starting to actually charge some of the lowest prices between 9 and 5. And then they spike up at 6, 7, 8 o'clock, and then they go down, but they don't go down as much, because again, in California, we have a lot of electric vehicle charging that those devices are set to charge at night. As far as I'm aware, Tesla does not have any real-time pricing algorithms enabled in their software to go ahead and change based on monitoring energy prices, because most meters don't actually have real-time energy prices. All CMP and I believe Emera have the ability to transmit that information, but they actually don't do it because, I don't know, there's a lot of socioeconomic issues that are surrounding that. So I know CMP a few years ago got sued by Brunswick, Maine, because they didn't want the smart meters to have information about loads and whatnot. So, there may be some pushback on that, but I don't know.
Do you think there'd be issues with them jacking the price up at certain times of the day just to try to make a quick buck?
So the question is, would there be issues with them jacking prices up? Absolutely not, because you can't jack prices up. PUC is monitoring you. So all the energy costs are based on what the ISO New England can charge, and what they do is they get contracts to go ahead and say, we'll buy power at this price. And then if there's more demand, it's at a higher price, so get more generation to come online that is not as cost effective. So that's going to be based on the cost of the generation, which is at LMP, that local marginal price. And then they'll add on a fixed cost adder to that so that Emera and CMP can stay in business, and then that'll just be transferred to the customer. So if it's real-time energy pricing, it's going to have to be based on something from ISO or something like that. If it's based on CMP at real-time energy prices or Emera, the PUC is going to be monitoring that, making sure that they don't do anything sneaky, because things like that have happened in the past, and that's too well monitored at this point.
So the PUC doesn't monitor then those private energy companies that you can buy your power from?
So the question is, does the PUC monitor those private energy companies? They don't monitor the generation at all. The generation is, hey, there's tons of generation. You can buy from generator A, generator B. You're not required to buy from them, but they monitor the utilities because they are monopolistic. Maine Independent Station has to compete against all the other generation to provide their energy that's in the area. But Emera Maine, Central Maine Power does not compete against anybody. They're the only ones that supply power to your home. So they're monopolistic, so that's who the PUC monitors. Generation, they do not. Now, if you are in a regulated state, which means generation is owned by the transmission companies, that is monitored and the rates are approved. But not in New England states. No, it's not monitored.
Well, what are we, because we have those power companies like, I think, Green Maine or Think Green, you know what I'm talking about?
Yeah, so the question is, do we have these power companies? Those are aggregators to kind of, they buy bulk power that's green or that meets certain criteria, and then you can buy that, you can come into contracts and agree with that with Emera Maine or whatever. And so what they do is they'll just say, okay, well, you're willing to pay more money for green power, so they'll just do contracts, and so they'll be the middleman essentially in terms of, all right, we're going to buy all renewables, and so Emera will just contract to buy 1,000 megawatt hours of green power, and then green power will go out and find the individual generators that meet those criteria.
So those companies, some of them have been shut down for fraud because they're the ones that
That's different. If there's fraud that's happening with those companies, that's not monitored by the PUC.
shutting them down though?
It would not be the PUC. That would be basically attorney generals that they're committing fraud. That's a legal thing as opposed to a PUC. Although PUC does have some enforcement availability, they don't have the same. If you do fraud, you're going to jail. If you charge people higher rates, the PUC is going to say, okay, well, you can't charge higher rates anymore, and you got to fire certain people. But most people aren't going to jail because they charge too much. That's just, they'll basically say, no, your rates can't be increased that high.
Because you hear about them they'll sign people up, and then they get a bunch of people signed up, and
Yep.
they get a power bill for
Yep.
$500.
But that power is actually still delivered through Bangor Hydro. So the bill actually gets all sent through Emera Maine. You would not be getting a separate bill from
But
them.
the PUC's not regulating
Nope,
people.
they don't regulate those people, nope. Okay, so if you're a big utility, industrial user, commercial user, you get hit with what is called a demand charge. So the utility has to build a system that can provide the peak power that's consumed on the grid. And if your power peaks up much, much higher than anybody else, the system has to be built to handle that. So even though it's not being used to that, it still has to be designed and built. And so the utility wants to get paid for it. So they do this demand charge. And it's usually, not always, but usually the highest power draw for 15 minutes per month, and you pay a fixed amount, again, to pay back the fact that they had to construct that. It's a minimum value, which may have a ratcheting effect. So if any of you work with a ratchet, it goes in one direction, tighten or loosen. This is a tighten. So if you go at 800, let's say you used 800 kilowatts for, 25 minutes or something like that, it locks in at 800, and then it goes down to 400 for the next 45 days or whatever. Then the next time it goes up to 1,000, so it ratchets up. So it just clicks up. It doesn't go back down to 800. It stays at 1,000. Usually it stays for a year, sometimes 2 years. So people are incentivized when there's going to be a lot of load at a facility. They try to shut down as much as they can because they don't want to pay for that extra year based on that. Another one that you would be charged, and this is again only if you're usually a large industrial user, is for power factor. If you look at, and if you remember when we have our current is going to be determined from our S, which is going to be determined from our P plus our JQ. The reactive power that the system has to provide is dependent upon the amount of reactive power that goes. So if I have a bigger I because I have a bigger Q, that means I have greater real power losses on my system because my magnitude of my current is larger. So because of that, the utility has to pay a much higher, they have to pay for the losses in the system that they're not quantifying because they're not getting paid for the VARs you're demanding. They're only getting paid based on the amount of watts you're consuming, so they'll actually charge you to include those lots, not those losses, I should say. All right, so now we have a sense of what we need to do for our costs and how companies get paid. Let's look at some very basic, simple stuff, and let's go with the easiest one. This is simple payback. If you're going to invest a certain amount of money to build something or to implement something, and you want to calculate what its annual savings are, or you know what its annual savings, maybe it'll save you $200 a year, $200 a month, whatever, you can figure out just very simply what the minimum amount of time it's going to be based on this equation. I invested $1,000, it saves me $200 a year, so it's going to take me 5 years to pay that back, okay? That's making it much, much simple. Your general rule of thumb is 5 years. If you invest in something and what is the likelihood it's going to last greater than 5 years? Probably not that great. They tend to make changes, companies move on, changes are implemented, so it doesn't last. Think of your computer or your cell phone. Does anybody here have a cell phone that's greater than 5 years? That would be a stretch. How about 3? Probably none of us have 3. I would say I have mine that's older than 3 years old, but that's, you know, atypical. Most of us get new phones every year, right? So if you think of the payback concept from that, you're not worried so much about that. You just want the latest and greatest. But from an investments perspective, if you're outlaying a lot of money, you want to know that you're going to get paid back in a reasonable amount of time. You don't include the lifetime of a system. That's hard to predict. You're just going to basically say that the lifetime of the system is essentially how long it's going to take me to pay back. The system is worthless. And more importantly, if you're saving $200 a year, it's not including the fact that you're going to have inflation that's occurring. So that savings may look worse or better depending on your perspective. So you can do this simple rate of return, which is you can divide 1 by the simple payback, or you can take your annual savings divided by your investment, and that essentially tells you the number of years that it takes to pay that back. So let's take a look at a simple example. We have a 3 kW PV system. That's what it's rated to produce at max sun or peak sun, and you'll start to hear more and more about those terms in a couple weeks. It has a capacity factor of 25. So remember, capacity factor means it's running full out 25% of the year. It costs $15,000 installed. That's for the rack, the inverter, the mounting of the system, probably on your roof, because 3 kW is pretty small. And you can save, or if you don't buy power, if you buy power from the utility, you're going to pay about 18 cents a kilowatt hour, which is, you know, kind of close to the going rate for what we do for utility. So we want to figure out what the simple payback is, and then what the simple rate of return is. So what we're essentially trying to do is calculate how much money we're going to save per year, okay? That's all we're trying to do, and that's why we need to know the size of the unit, the capacity factor, which is going to tell me how many kilowatt hours this facility is going to produce, and I also need to know what it's going to cost for power, because I don't have to buy power anymore at 18 cents a kilowatt hour. It's going to be defrayed by the fact that I've installed my PV system. So first thing I need to do is figure out how much power I'm producing a year, almost 6,600 kilowatt hours per year. Then I figure out how much it costs to buy that power from the utility, so almost $1,200 a year. So I take my PV system, which cost me $15,000 to install, and it saves me almost $1,200 a year, and it's going to take about 12.7 years for this system to be paid off. Again, just a simple payback without any inflation effects included. Rate of return, 7.9%. So your investment rate returns 7.9%. So the question is if you're a renewable energy consumer, supplier, provider, would you do this? Most people would probably not. That's too long of a payback. Unless you're really somebody who's green and is touting the concept of, I want to have the newest widget on the block and I want to be doing something unique, most people would say 12 years is just too long to get that payback. Okay?
They're really that expensive?
Pardon?
They're that expensive, or is that kind of an outdated number?
Yeah, so the question is are PV systems that expensive? It depends on a lot of factors, right? So not only do you have to pay for the modules, right? So you need multiple PV modules. You're going to have a rack to buy that. You're going to have an inverter because the output of a PV system is DC, so you need to invert that to AC. You're going to have to run all the cabling. You're going to also have to mount it, right? So is $15,000? It depends on how difficult it is to mount to the roof or to the ground or wherever you're talking about. So $15,000 is not that much, as a matter of fact. That's probably a pretty ballpark good price for what a PV system would cost you. And if you think about it, for those of you, anybody have a home, how much does it cost to put a heating system in? Heating system with a lifetime of what? Close to 20 years is going to be at least $15,000, right? So if you're trying to compare apples to apples, $15,000 seems like a lot, but it actually is not that much. Anybody here had work done in their kitchen or a bathroom? $15,000 kitchen is pretty darn cheap. So seems like a lot of money, but that's only because we think, hey, we pay so little for electricity, we shouldn't do that. But in terms of the actual cost for upgrades, it's not that much. And anybody here have a car that they bought less than $15,000? Couple people?
Paid less than $15,000?
Yeah.
Oh, God, yeah.
Okay. Well, that's why we're college students. But I bet most of you within 5 years will have cars that pay more than $15,000. People shake their heads. We'll see. Come back and see me in 5 years and see what it is. We'll see. All right, so now we're going to start getting into the concept of the time value of money and interest rate. So money has two aspects of it. Obviously, how much you got, but then how much is that money allowed to quote unquote grow? Because if you have $1 in your pocket and you leave it in your pocket in 5 years, that dollar is still $1, except it's not, because inflation has started to eat into the value of the dollar. And if you say, well, I don't want to have it eat into the value of $1, I would like to invest it, you're certainly welcome to do whatever investment vehicle you want, but that dollar may be worth a little more if you invest it, which basically means you're losing control of it. Every time you bring your money to the bank and you deposit that money in the bank, you are allowing the bank to have control over it, which means they can lend it out. They can invest it. So that's why when you get a 2% savings account, the bank charges 6% to borrow money because they have to make a profit and the difference between the two. And it all has to do with convenience, right? I'm borrowing money to buy a car and I have to pay it back for more than what it's worth. And it has to beat the cost of inflation. So that's why if inflation's running around 3%, you have to at best beat the 3%. Otherwise, it's not worth it. So savings accounts, we get 2%. We're losing money. So every dollar you have in a savings account is actually less valuable today than it was yesterday because of inflation's biting into it, even when you include the 2%. That's why when you look for investment vehicles, you should at the very least be looking to beat the inflation rates, plus the fact that if you've invested the money in a vehicle that doesn't have any tax advantage, you also have to include the fact that you're going to be paying taxes on it. So when you think about the return on the stock market, 8%, 7%, you should be hoping to get at least 8% because if inflation is running 3%, plus you have to pay, maybe 25, 30% of your gains in taxes, you can see how 8% doesn't seem like all that much. So that's why when you start to do these calculations, you can start to see, hey, wait a minute, 8% sounds like a big number, but in actuality, it's not a great break even. So, and I do this a little bit because if you think about, we talk about time value of money. When you are an investor, if you're only looking to get 8% and that's not in a tax advantaged account, you're probably not going to get that far ahead. But if you do 401k, 403b, an IRA account, those are tax advantaged, so you only pay when you withdraw the money or when you put in, and so a lot of the money can grow without the penalty of taxes being taken out. All right? So that's why for most of us who are in this room, or most of you all who are in this room who are younger, you're way better off to do a Roth version of any account, because all that money goes tax-free. So when you take it out, you don't have to pay that 30, 40, whatever percent based on your federal and your state income tax rates. So something to think about. So I talked a little bit about I borrow and I pay interest, and then if I invest money, I expect to be returned. Again, when you're buying stocks and bonds, or when you're buying a mutual fund, you are lending money to those companies, the Apples, the Googles, the Facebooks. You are lending money to them because they are issuing stock, and then they get paid on that stock so that they can actually invest in their business. So when they do a stock offering, they're hoping to get so many $1 billion, so many $1 trillion in the case of Apple, right? You're trying to get a certain amount of money so that you can invest in your business and grow. At some point, and again, this has changed a little bit because of technology, at some point, the business has to make money, right? Apple has to make a profit. Microsoft has to make a profit. Google has to make a profit. Other companies like Uber, do they make a profit? I don't know. I mean, I don't know enough about the market to do that. But if you continue to invest in those companies, at some point, you have to start to say, well, the stock is not worth anything. Tesla is an interesting case because their stock shares, I don't know, $400, $450 a share, but have they made money? I think they've made money 1 or 2 quarters in the 10 years that they've been in business. So the concept is, it's a cool idea. I own Tesla stock, but it's hoping that in a couple years, the stock's going to be worth $4,000. It'll be like Amazon. So you're willing to keep investing and buying the stock with the hope that that's going to continue to grow. So that's kind of the idea, but you're only buying the stock, hopefully, because you're expecting it to be worth more in the future. Sometimes you buy stocks also to limit your losses, but that's not always a good approach to do. So here's compound interest. So compound interest just basically says I get interest on my interest. Simple way to describe it. So if I have a 5% rate of interest rate, if I have $1,000 after year 1, I've got 1,000 plus that 5%, which is compounded annually, I get 1,050. At the end of year 2, I'm getting 5% here on that additional $50. So I don't end up with $1,100. I have $1,102, and then $1,157, and $1,215. So after 4 years, right, I end up with an additional $15.51 because of compounding, interest on my interest. Okay? You only get interest on your interest if you leave the interest that you've gotten, you leave it in there to get additional interest. All right? So that's that compounding effect. You've got to leave it in there and not touch it. So let's convert that to a formula. So EOP is end of period because sometimes you annualize your interest rate, so it's an APY or an APR. Sometimes you do it monthly, quarterly, annual. I mean, it could be just all kinds of different things. So we'll just do it generically as end of a period, and the period can be what it needs to. So either the amount is owed to you or you owe it to somebody else. So you owe P, and then you're taxed or you're charged interest based on that. So that is P times whatever interest rate it is. Then that gets added to the original principal. So P here is the principal. That becomes the amount owed for the next period. And then if you add interest on that, it's P times 1 plus I times I, all the way until you get down to this equation here. So what we can do is we can actually take our principal and figure out what we owe on it, by simply adding 1 plus our interest rate and raising it to the n, which is the number of periods. So we're going to use that, and we're going to use an engineering economics term, which is sort of the subscript as much as we can. So F here is our future value, P is our present value, and I is either our discount or our interest rate, and N is the number of periods, years, whatever. So you're going to find this future value here based on a present value, an interest rate, and the number of periods. So we're going to define a function or a term which is finding a future value given a present value based on just this equation here. okay? So you can actually look that up in tables. Those are actual data tables that are available to you in any engineering economics book. In Excel, they actually have those formulas built in for you. So you can actually find an F given a P, so you specify a present value, an interest rate, and the number of periods, and it'll shoot out the future value. But it's all based on this equation here. So we can, instead of doing it every end of period, we can do it very simply. If we had that $1,000, our interest rate was 12%, and we had 5 years, we substitute in for our P, our I, and our N, and we get a future value of $1,762 for our future value. Also, we talked about equivalency, right? So the idea of equivalency is, again, you don't care when the two are together. You can say P and F are equivalent based on your calculations. So if I asked you for $1,000 today and I gave you $1,762.34, that should be a zero-sum game. You should essentially say that's a break-even deal. There's no advantage or disadvantage to you, just purely on the analysis that's run. Now, if you don't think you can get 12%, then that's a good deal. But if you think you can get 20%, that's a bad deal. So then you have to reassign or reevaluate your numbers based on what's happening. So let's take a look at equivalency. Excuse me. Would you rather have $12,000 now, $1,200 now, or would you rather have $1,500 now? Or 5 years from now, I should say. We're going to assume that you can get a 6% interest rate. So if you take your $1,200 and you put it someplace, you're guaranteed to get a 6% interest rate. So we'll do a future worth calculation or a present worth calculation, which basically means take that $1,200 and move it to the future and see if it's greater than or less than $1,500. The other way we can do it, which should give you very similar results, is take our $1,500 in the future, move that to the present time, and see if it's greater than or less than the P. So over here, by moving my present value to the future, it's $1,600. $1,600 is greater than $1,500, so that means I'm better off to have $1,200 today than the $1,500 in 5 years. Let's compare it the other way. So I want to take my $1,500 and move it back in time using my function here. That is $1,120. That is less than the $1,200 that I have today. So either case tells you it is better to keep the $1,200 today and not accept the $1,500 that's being offered to you. So take the $1,200 today. So I mentioned this a little bit at the beginning when we discussed the outline. There's an interest rate, which usually moves money forward in time. So you take a present value, and then to figure out what that money is going to be worth in the future. So that $1,200 is worth around $1,600 in the future. That's an interest rate. A way to look at it differently, but kind of similarly, is to take the $1,600 or so that we had out in the future, and what does that need to be discounted by as a percentage, discounted by every period, so that I can figure out what it's worth today. So discount rate or interest rate is the same, it's just going in a different direction. How much do I have to discount the future value of something to bring it back to a present value today? The interest rate or the discount rate is the same, it's just they're going at it in different directions. So if you were to think about it, your interest rate goes this way, your discount rate goes in the backwards direction, okay? So if I'm going to have a projected savings of $10K in 5 years, what do I need to discount that by to figure out what it's worth? Well, if I have a 10% discount rate, that's worth $6,200 today. If I have a 20%, that is $4,000. So when you think about, it's a little bit of a different thinking, right? Because what you think about is you say, hey, I'd like as high an interest rate as possible because that means my money is going to be worth more in time. But a discount rate is the opposite. The discount rate says, well, if my discount rate is lower, that means that I have a higher present value for an item than I have for the future. So they kind of mean the same thing, but the present value looks a lot higher. So that means you have to have a higher present value to make it worthwhile in the future for a lower discount rate. By the way, does anybody know car vehicles, what a lease rate is? That's a good opportunity to look at an interest rate or a discount rate.
You mean like how a lease works? Or?
Nope. Pretty much everybody knows how a lease works, right? You go get a car and you get a set of keys, but you actually don't own the vehicle. The car company owns the vehicle, and you pay a certain amount of money to drive that vehicle, and then at the end of the lease term, you turn it back in. Hopefully you haven't exceeded the mileage and the wear and tear criteria. Anybody know what the interest rate is?
Oh, it's probably a lot.
It's like 12 to 15%.
I think it's 14 to 18%, but nobody knows exactly. You know why? Because federal law states that you must reveal what an interest rate you're going to charge when people buy something from you. If somebody borrows something from you, there's no federal law that mandates that. So if you look in your documentation as to what the effective interest rate is, good luck finding it. So I'm not saying that leases are good deals or bad deals. It's just that when you borrow something, it's very different than if you do that. And so if you were to go and, I don't know, anybody ever been to a pawn shop? I mean, the idea of a pawn shop, right, is you're going to either sell it or you're going to pawn it. So you basically, you're putting your thing up for collateral to get a certain amount of money. You're just borrowing the money, right? So they can charge very different rates than otherwise. Check cashing, right? That's the same kind of concept. You're borrowing money, so they can charge very different rates than you would get charged if you were buying something. So something to think about.
Student loans don't have to tell us their interest rate?
No, student loans do, because you basically are borrowing money. They're giving you something, right? And then you're borrowing. So you're not. The student loan is different because it's essentially it's an unsecured loan, right? So student loan is, the fact that you're a student will lend you $10,000 to essentially, hopefully, buy a degree. But that's a case where it's an unsecured loan. So in that case, you're not really buying anything, but you're not really borrowing anything either. Nobody's giving you the keys to a car or a house to borrow. They're just giving you money so that you can go to school. So that's sort of a hybrid case, and in student loans, I think it's a different federal law that says they must reveal the interest rate. Because again, you're not borrowing something. So you're not borrowing a vehicle. Obviously you're borrowing money, but it's different than borrowing a car or something like that. You're not really getting something from them. You're just saying, I promise to pay back this money. So they're like, okay, fine, we'll let you have this money. So works a little differently. By the way, student loans are one of the toughest loans to get X'd out. You can't file bankruptcy from student loans for what it's worth. Federal government says you cannot do that. You can under disability service conditions, but if you try to run from your student loans, you will not. So don't even try. Okay, cash flow. So again, we always have to have a positive cash flow. If not, we don't eat, right? The businesses will go out of business. And so cash flow can also include borrowing money from a company to continue to make payroll or to continue to buy material, or like in the case of Uber, to keep paying drivers and keep the technology and to keep investing. At some point, the idea is that the company will make enough money that they'll be able to have a positive cash flow, and then they'll be able to build that. Most of the large technology companies, I don't know this for a fact, I should be careful saying this, but many large technology companies probably don't even care if they make a profit. They really just want to keep pushing the stock prices up. And so a lot of CEOs now, that's what their focus is how do I keep my stock price elevated, because that makes it so that I get bigger bonuses. Do I make better widgets? Do I make the company more money? Well, if my stock price is higher, the investors are happy. Nobody's going to complain. So it's a slightly, I'd say, major change in how companies are run from maybe 20, 30 years ago. But most of us, right, when we look at business and the effectiveness, what's the number one thing most of us look at? How did the Dow Jones do today, right? Everybody know what the Dow Jones Industrial Average is at? I bet you most people have an idea that it's in the 27,000 range, right? But does anybody know how much a quarterly profit Apple had last, or Facebook, or Amazon? Amazon's trading over $1,700 a share, but how much money did they make last quarter? I don't know that, but I can go look on the stock price. So it's just the way that how our world, our excessive information works.
So what happens when they want to cash in on their money? What happens to a big group of people? That's the stock market.
If a big group of people want to cash in on their money, they just try to sell the stock, and then hopefully there are buyers out there that are willing to buy the stock at that price. If you have too many people selling at once, then you can't actually sell your stock. People won't buy it at the price, or the price gets dropped so much that you could potentially lose money. That's why a company like Berkshire Hathaway, which is Warren Buffett's company, they buy $50 billion worth of stock at a time. They can't just do it one at a time because the prices would go through the roof, or they can't sell it. So they have to sort of do it in a way that's very subtle, and they just have to sell it in blocks or chunks. Can't just sell it all at once because it would move the market too quickly. So here's the idea of a cash flow. Cash flow is money coming in and money going out. Positive money is money that comes into you. Negative or below the line is out. So you show direction of money, and then you also show the period of money and when it is going in or out. This is a uniform cash flow, right? So you borrow $10,000 and you're paying back $500, whatever, a period to pay it back. You can also come up with an equation to find a future or present value, for that matter. You can find a future value, makes it easy to do it that way, based on summing all those payments, and then we're going to pay the interest rate with it as well. So we use a summer with our period starting at 0 in this particular equation. So here are sort of the summations showing you with the interest rate. So this is, again, the end of the period, but now we're getting some money going out, so it looks slightly differently. We're using an annuity. That's what the A stands for. It used to be an annualized number. Now just an annuity means any continuous uniform cash flow payment. So here is a cash flow. This is not an annuity because you can see that the numbers are changing. So my discount rate, when I move my money back at year F5 or forward, I can go either way, it's 12%. In year 0, I pay out $2,000. In year 2 or period 2, I pay out $2,000. In year 3, I get $2,000 back. And in year 4, I get $4,000 back. I would like to know how much money I should be getting back in year 5 based on this 12% interest rate to make this equivalent. So I take my $4,000 and I move that forward 1 year. I take my $2,000 and I move that forward 2 years because that's in year 3. My $2,000 that I had to pay out, I have to move that back 3 years, and that's a negative because of the negative arrow. And I do the same thing for the initial payment. When I do the math, at the end of year 5, to be equivalent, I should get $654.26 to make this equivalent. So this is just to sort of summarize, go back to this finding an F given a P, right? Find the future value given a present value. We can modify that slightly by inverting it and then defining this term beta. And you'll see why we use beta in a little bit because, the math gets a little bit easier when you use the term beta. So beta we're going to define as 1 plus d to the minus 1. If we raise beta to the n power, then our 1 plus I to the n is also raised to that power. So here's another cash flow, and we won't have to go too much, but we want to know what the future value is at year 8, and then what the present value is given a 6% discount rate. So we bring everything out to year 8, and we see that with our discount rate of 6%, we're just under $952. Then we're going to find a present value given a future by multiplying by beta, right? Or beta to the n. And so we can multiply by, let's scroll this up a little bit. There's 2 ways we can do it. We can take all those annuities and move them to the present value and end up with $597, or we can take this value and multiply that by, take this value and multiply that by the inverse of beta to get that value, which is the same approach. So those are equivalent. So bringing it forward or backwards, right? Using your annuity and bringing it forward in time, or moving it back in time, and then just finding your present value, giving your future value, or vice versa, you should end up with the exact same results. So here's that equation now for doing present value. So we're just going to multiply our annuities by our beta function here. And also, if we find our future value given our present value, we can scroll forward and find our present values that way. So let's say we have an investment that pays $1,000 at the end of year 1 and $2,000 at the end of year 2. Your interest rate is 10%. That's what you're expecting to be paid. The question is, how much would you be willing to offer somebody to get this deal? What would be the maximum that you would do? So if you bring everything to a present value for your year 1 and then your year 2, again, I'm multiplying by my beta because I'm bringing those terms back. Those are my annuities. If you want to get an interest rate of 10%, you shouldn't exceed $2,562. If you pay more than $2,562, then you are not getting 10% rate of return. So if somebody approaches you and says, I would like you to give me $1,000 at the end of year 1, and I'll give you $1,000 at the end of year 1 and $2,000 at the end of year 2, here's what I need from you, then you get to decide if that's a good investment for you or not. So just in your own personal decision making, right? Do I want to buy something or do I want to lend money out? Maybe not, such a personal thing, but in terms of buying vehicles, buying, heavy duty appliances, whatever you want to do, take a trip, you can consider, what the advantages and what the costs are to you versus looking at the present value, which is not always a good one, but normally it's looking at annuity, put it on your credit card and then figuring out how much that's going to cost you over time. That's a good way to do some sort of hard looking at whether you should do something or not. Not always as fun, but you'll definitely make smarter financial decisions that way. So net present value is another great way to compare alternatives. Do I buy a car that's going to need this much maintenance and last this long? Or do I buy a brand new car that's not going to need any maintenance, but I have higher payments? So the net present value of an investment is comparing what your expenditure needs to be and what its present value of the return will be. And the delta should be a positive number. Sometimes it's a negative number, and sometimes you can't help that. For example, pollution controls. For a while, a lot of coal companies were putting baghouses on their exhausts, and they were required by the federal government to do that. So your net present value was going to be negative, so you were looking for the lowest negative number, right? The closest to 0 that you could find to do that. So here's that investment that we talk about. Somebody is asking you for $2,400, and they'll give you $1,000 at the end of year 1 and $2,000 at the end of year 2. Well, you did your calculation, and you saw that your present value for that is almost $2,562. So you actually net a positive $162. So this would be a case where you'd say, yeah, this is an investment I'm willing to make because with my 10% rate of return that I can expect to get anywhere else, I'm still going to make an additional $162. So this would be a good investment. I talked mostly about this, right? So net present value, you can compare any different investments you want. Keeping the money in your pocket, putting it in the bank, investing in the stock market, those get harder and harder because the rates of return aren't guaranteed. But if you're looking at averages over time, you can feel pretty comfortable about that. And then, as I said, if you have to invest in pollution, then you're looking for the smallest one. So let's look at the present value of a loan. You want to borrow money, and you predict that you're going to be able to pay $1,000 at the end of year 1, $2,000 at the end of year 2, and $4,000 at the end of year 3. Maybe you're doing a candy making business, and your company's going to grow by so much, and you need a certain amount of money up front, and then you have to make a decision based on an 8% interest rate of what the bank can get elsewhere. So how much should you be asking for? Well, I calculate my beta, which isn't going to change, right? Beta is 1 plus d to the minus 1. and since your discount rate's not going to change, it's going to be a fixed 0.926. Then I just have to bring back or bring forward in time each of those end of year expenditures. This one I'm bringing back 1 year, 2 years, so I have to square my beta, and 3 years, so I have to cube my beta. So that present value is $5,815. So from your perspective, you would want to get paid at least $5,815.93 to make the investment. So your perspective is, I'd like to get more than that, right? If you're the bank makes more money if they lend you less than $5,815. So again, when you're doing the calculations, the banks can do this stuff, right? They have, Excel spreadsheets. You can do it, as a matter of fact. You can do all this stuff. But if you're trying to go through and you're trying to make an investment that's a little atypical, you can have a determination about whether it's a good investment for you or not. Now, this work also just looks at things in terms of you're definitely going to get paid back, and your interest rate is going to be fixed, and it's not going to change. In reality, right, those are other factors that you need to include, because that is called risk. And risk is something that you need to be able to quantify. So the risk in this case is another way of saying 8%, right? How much can this person who wants to borrow this money, or how much can this bank get elsewhere by doing this? If the person can get a better interest rate than 8%, then they're going to go elsewhere and get 6%. If the bank can get a better interest rate, 9%, 10%, then they're not going to do this. They're going to accept less risk. Or they're going to accept the same amount of risk, but they're going to expect a higher rate of return. That's why venture capitalists, when they do investing in these startup companies, they want 600-700% interest, because the risk is tremendous. But they know that they've got a captive audience, because there's only a few people that are actually capable of investing that kind of money. And they realize there's a high likelihood that they're going to lose it. So we already talked about the uniform cash form with annuities, and we're going to go ahead and find our present value using our beta function here, just bringing all those values back. So now we're going to do a little bit of magic with our beta term. So let's say that our beta is always going to be between 0 and 1, which it should be, right? Because you're not going to have a negative interest rate. It should always be a positive interest rate. So if it's a positive interest rate, it's always going to be between 0 and 1. So if I do my infinite summation, and I don't know if this is Taylor series, I always forget the one, but if you do an infinite expansion, you're going to end up with 1 over 1 minus beta. If you truncate that series and stop it not at infinity, well, you can take your infinite series and then subtract from it your beta to the n. So doing a little bit of work will give you, for a truncated series, 1 minus beta to the n divided by 1 minus beta. Keep in mind, again, that beta is equal to 1 minus the discount rate raised to the negative 1 power. So I can do that, and I can expand to find my present value given an annuity as this equation here. So as I said earlier, the reason why we like to write things in terms of this beta is the math just gets a little bit easier if we write it as a variable. So we'll find a present value given an annuity of 1 minus beta, which again, beta is 1 minus the discount rate raised to the minus 1 divided by the discount rate. So if you want to figure out how much it's going to cost for you to buy that $200,000 home and pay it back 30 years, you can use this formula, and it can do a fixed cost, and it'll be a fixed amount. So this is just formalizing it. This is the present value function, finding a p given an a, using our beta term, or if you don't like the beta term, you can substitute in your 1 minus d to the minus 1 into that equation there. Okay? I also showed you some different terms. This is in Excel. I think it's written in Excel that way. P given A, discount rate. Or you can go backwards, find an annuity given a present value, inverting it. And then if you want to convert that to an annual amount, you can use this formula here. So just sort of summarizing, we have a present value function for annuities. We have a present value function given a future value. We have a future value given annuities or given a present value. And then our capital recovery factor, our CRF, again, just paying back the capital over, it's not the fixed charge rate, but it's paying back what we expended to purchase or construct the plant, is find an A given a P, all right? Now, I said this is term fixed charge rate. It's not 100% valid. This is fixed charge rate only if you're going to pay this amount back in perpetuity. So essentially what you're doing is the capital recovery factor is not only going to include paying back the plant, but also you're going to have to do some upgrades and maintenance. So perhaps that money that you're paying back, you're just going to continue to pay back because you do plant upgrades or whatever. So it's, you know, in the real world, you would have you're going to pay the plant back, but you're going to continue to have to invest and upgrade your equipment. So that's why you would essentially assume that you're paying it back in perpetuity. For those of you who like the TI-89, so I talk about TI-89, there is a financial modeling calculator that you can download and install, and you can run that. Most people now are using Excel, so those are built-in equations into Excel. So you can insert an equation, and there's a financial tab that has all these equations in here, and you'll find present, future, annuity, interest rate, discount rate, all those terms that we talked about are defined there. So, equivalence, we want to be able to say that either the annuity with A at that period or B in that period are going to be equivalent to each other as long as their future worths, or pretty much any point in time are exactly the same. So here's an equivalence case where we have an investment that in years 3 through 7 are paying back 7%, or in year 2 we'll pay $8,240. Our discount rate is 7%. So let's compare the present values. In the first case, right, we had to move those 4 terms or 5 terms up until year 0. We end up with $7,162.33. In case B, same thing, but we're just moving it up, that one amount up 2 years. So these are the same because their present values are the same. So let's look at another example to see about equivalency or not equivalency, right? So we've got 2 separate motors, motor A and motor B. They're both rated 100 horsepower and are going to last for 20 years. By the way, can you tell which is the more efficient motor? Is it A or B? Yeah, if you look at B, right, B needs 77.5 kilowatts, continuous consumption of power, to produce 100 horsepower. Motor A needs 79 to produce that same 100 horsepower. So motor A needs 1.5 kilowatts more to produce 100 horsepower. And it may not be as obvious, but costs, right? You would expect a more efficient motor to be a more expensive motor than a cheaper one. There's not a lot of things that people can do. Most of the time with premium efficiency motors, they'd use copper windings, maybe slightly better cooling, so maybe a slightly larger casing. The other thing that you see people do too is they use more efficient bearings. So better bearing technology may reduce some of the losses, because the big thing with bearings, right, if they're running at 1800 RPM, that's a lot of friction losses on that bearing that's constant. So reducing those, or having a nice smooth shaft, the smoother the shaft is, the less windage losses. A smooth shaft you don't think makes a big deal, but if it's 1800 RPM spinning constantly, the air actually on the shaft creates a drag. And if you're at a big enough facility, I've worked at many nuclear power plants that their generators that would run at 3600 RPM, they are surrounded by hydrogen. Anybody want to guess why we would cool with hydrogen? Where does hydrogen end up on the periodic table? It's a Pretty small number, isn't it? So, isn't it number 1 on the periodic table? So it's a very light gas. There's only 1 electron, so it has very little friction or windage losses because of that. You don't see a lot of those because they're very expensive to maintain, but very large generators, they use hydrogen for surrounding the generator. They actually use that to cool it, but that's, you know, a more detailed. Well, the generator would be enclosed in the case, would be inside of a case, and then they just seal it all off so that all the cooling goes through some radiators, and so all that's inside there is hydrogen gas. Yep. So let's look at motor A. So it's going to run 1,600 a year at 8 cents a kilowatt hour, so we're buying power pretty cheap. It's going to need about $10,112 a year of operation, which is not that far off, right? 1,600 hours of operation a year is not even 8 hours a day, 5 days a week, right? But it's running that much full out for that period of time. So this electric motor is over $10,000, so you can see why we talk about efficiency as a big deal. So if we take the cost of $2,400 plus $10,000, and again, we are not assuming any escalation in costs of energy, we can bring that to a present value of today. With that motor running for 20 years, it's going to cost $86,000. Okay? We do the same thing for B, and the present worth is $88,489. No, this is A. There's a typo, I apologize. This should be A, not B. Let's do B, and instead of the $10,120 or whatever it was, it's only about $250 less energy consumption a year. So we're going to do the same thing and do our present value. So our present value is $87,355. So there's not a huge savings between the two, but if you go with the more efficient motor, motor B, you're going to save $1,135 over 20 years. The trivial amount of savings over 20 years would probably say don't bother because 20 years is a long time, but you get the idea of how to do the calculation. And that was my last slide. So any questions on our discussion today about Introduction to Engineering Economics? It's going to go a little fast, but the hope is that it'll make more sense as you go through it. The other thing I will add too is we're trying the different technology here, so even though you're not seeing my smiling face, the audio quality should be good, and the video quality should be better than what you're seeing. So in the first few classes that I taught, I was using very similar technology, but I had to use it as a specific location, and so our department has made some investments to hopefully provide you with a better experience in terms of looking at the slides and hearing the video or hearing the audio. You don't hear video, you hear audio, and then also seeing some of the quality. So we'll do that again for the next class, and then the following 3 classes after that where we'll cover wind, and then I'll be curious to see feedback. Do you prefer to just do everything online where you can watch the videos at your leisure, or coming in? In terms of the quality, it shouldn't make a difference. It just depends on the flexibility moving forward. So this is trying to take advantage of technology that Professor Dvorak and I talked about at the beginning of the semester. So with that being said, thank you very much and have a great day.